Michael Tolbar, who is going to talk to us about novel microwave cavity designs and coupling to spins, magnons, and phonons.
Okay, thanks for the invitation. It's great to be here. I'm here as I lead this research group. We're a fairly big group because we have funding from 2 ARC Centers of Excellence. So our lab has 3 dilution fridges and about 7 4K systems, and 1 system that could be upgraded if we get more money to another dilution fridge. So we've got quite a lot of magnets and a large collection of diagnostic equipment. What we don't do is fabricate devices, but we do collaborate with people and get their devices and measure them. We call ourselves the QDM Lab, Quantum Technologies and Dark Matter Lab, and the difference between our lab and a lot of other groups is that we're not going down to really, really small scales because here's the lab, Quantum Technologies and Dark Matter Lab, and our main goal is to do these precision measurements, and this is the type of cavities we use, and we use big resonators because most of our experiments are for detecting fundamental physics. So our main focus is to look for new physics, and when you do that, you need big systems. But what you also need is the quantum technologies to read out your system. You need to be able to do things like squeezing. We've seen how magnons can do squeezing, or phonons can, and things like that. So we're very interested in getting these large systems into the quantum regime. We want to get phonons to the quantum regime to do tests on quantum gravity, large masses, and we're looking at large resonators to look for dark matter, and you can also use magnons to look for dark matter. This is the sort of systems that we use. High Q cavities, some sort of spins or atoms, and some acoustic devices. So, as I said, this is sort of our major push through my career is to be able to do these things, but of course then you do a whole lot of practical translational stuff as well. So the main issue is to improve signal-to-noise ratio, and that's why we need the quantum measurement. And hopefully one day we can find some new physics at low energies. So I wanted to just say a bit of history of how we started working on this. And this was my PhD project, and this is a big 1.5-ton niobium bar coupled to this bending flap, which is both tuned to 700 Hertz. So it's a coupled mode system. It's a coupled acoustic mode system where they both need to be tuned, and the idea is this amplifies a gravity wave that hits this bar. And unlike all the other groups at the time, we were using parametric readout with this reentrant cavity, and these reentrant cavities are very high precision sensors. When the gap moves, the frequency moves, and we would then we needed a low noise oscillator to drive this. So this is basically optomechanics between 2 coupled acoustic modes, and then this is your usual readout that you would do for any cryogenic experiment. You have to have a microwave amplifier. But because we had large power, we had to build an interferometer to cancel the noise at the amplifier. And this actual thing is a very sensitive phase detector. I'm not going to talk about it, but we ended up with a lot of patents and been able to build low noise oscillators based on this system, which came from fundamental research. So I like to tell people that fundamental research is essential because all our technology that developed from this microwave interferometer is all in the Raytheon defense radar in the US. So anyway, but this sapphire oscillator was an interesting device. It's a sapphire crystal, and you might say, where are the spins in this system? There's phonons and photons, but where are the spins? And so these sapphire crystals, very high Q, they're about as big as my fist, really excite these whispering Gary modes, get a few billion. And but how do we get a good phase noise and stability? Because when we built these, now they're in cryogen-free systems, and you can get them operating with, you know, parts in 10 to the 16 stability, and there's even commercial products based on these. But there, you know, when you get some stability like this, you need to have a temperature independence of frequency. And how do we get that? And this is, if you look at the crystals, you can see some here are doped with spins, and because they've got a certain color. And I call this the frequency temperature miracle for a cryogenic sapphire oscillator. And this is what got me into spin physics, because it turned out that when you go down to low temperatures, the lattice has a temperature dependence, but there was a magnetic susceptibility that cancelled that temperature dependence. So that was sort of a fluke. And this temperature turning point always occurred between 2 and 10 Kelvin. And then it was also independent of impurity, believe it or not. We have a paramagnetic impurity in there. It could be molybdenum, it could be Fe3+, it could be chromium, and we'd always get a turning point around there. So it turned out that it was just, and the concentration seemed to not matter. It could be parts per billion. The bigger the concentration, this would move a little bit, but it was T to the -1/4 dependence on the impurity. So it was like a miracle that nearly all our samples had this turnover point. And that's what started my career in this work. And all of this work for this gravity wave detector was optomechanics, photons coupling to spins in the sapphire, and we started learning solid state physics to do that. Now, in the current day, we've made a whole variety of resonators. There's our Whispering-Gowrie mode resonators. There's other types. And these reentrant cavities are quite interesting, where you have a gap. And when I was working on these devices back when I was a student, I always wondered what would happen if you had multiple posts. And with the event of ComSol, we could start investigating that. And with a good postdoc, we invented these multiple post cavities. The double post enabled us to get really strong couplings, and we could make lattices, and we could make even topological type things. Towards the end of the talk, I really wanted, this is a new type of resonator we've invented. It's a resonator with twisted boundary conditions, which gives us bulk modes with helicity chirality. So the first thing I want to do is some history of our work on coupled modes. And this is the first paper I wrote in my life. It is 1991, and I was tuning this high-Q sapphire resonator, and I saw all these weird effects. I asked a professor, and he said, in quantum mechanics you can have these cross terms. So I looked up the literature, and I found a Lagrangian technique to model microwave cavities, and in general you could come up with this, between two modes, these coupling parameters, and then when you get the equivalent circuit, you get this. So you have mutual inductance, mutual elastance, and mutual resistance, or Q. And they were able to model what I saw. And what I saw when I tuned these modes, and I was trying to build this tunable resonator to make a low phase noise tunable oscillator, I would see I'd get this strong coupling as they pass between modes. And then when I get really broad line resonance, I could see I could get Fano distortions like this. You can see this Fano distortion goes on the top, and when it gets to the bottom, it's like EIT. So it just turns out that this is just this cross coupling, and this resistive term enabled you to model this resistive coupling. And I could model everything, and I published a paper, and it was pretty much forgotten, but for me, it's my first paper I ever wrote that was pretty good, but I think it's relevant for what everyone's been talking about, so I just wanted to bring it up. And with the resonant detector, this was a parametric effect, so you get parametric back action, and we could cool the system with our electromagnetic signals, and we could tune the frequencies, and we could. So the big thing about these systems is, even though that people call it cooling, it's really cold damping, because you reduce the Q as well as the temperature, so you can't gain sensitivity. And we actually did the first resolved sideband cooling back then. And that was sort of missed as well, where we build these high Q resonators in the resolved sideband regime. And there was some more, we tended to build these big experiments. So that's where we're sort of, these big crystals. So we had learned how to, we had understood the strong coupling between modes and generating phanoresonances as a resistive coupling. And we had done quite a lot of this sort of stuff. And when it came to strong coupling between acoustic resonators, because we saw a talk on this earlier, we were looking at multi-mode systems, and we could look at, I worked out a way to do an N-mode system. So you could solve the frequencies, if there was more than one or two, but for the Q factors, you could derive a matrix equation and calculate the Q factors too. So here's an example of a more recent paper where we coupled spins with photons, and we could model the Q degradation and the coupling just with these formulas. The interesting thing is that if you want to do the frequency, you assume the Qs are infinity and you take these out and you equate this. If you want to model the Qs, you just equate these coefficients and you come up with a matrix equation, and you can easily model these Q couplings in your system. Okay, now some recent work on coupled modes. I'm doing this just because I thought people might be interested. Not talking about magnons yet. Well, we wanted to. This is the electromagnetic Aharonov-Bohm effect, a geometric or Berry phase. This is the well-known experiment of the Aharonov-Bohm effect, where you have a vector potential and a phase is generated over different paths. So you integrate over the path, and if you've got electrons coming around here, there's an interference shift based on the vector potential and not the field, because all the field's in here. There was another proposal in this sort of famous paper which looked at the electric scalar potential. And these days, people are looking at the gravitational Aharonov-Bohm effect, which is also a scale effect. So that's an analog to this as well, which I'm not going to talk about. So here you have a phase that generates over time. This is temporal. So this is a spatial effect, and this is a temporal effect. And so the proposal in this paper was to split two electrons, have one a Faraday cage grounded with no electric field, and one at a certain potential with no electric field, and then see an interference shift. This experiment hasn't really been done properly. There's one group that has attempted, but it wasn't really, and they saw some signal, but it wasn't really a clean experiment. So the proposal with some collaborators of mine was just to do the temporal measurement, just to make a Faraday cage and oscillate the potential, and you should see some shift on some side bands. And so we tried to make something that could do this. It's like the AC Stark effect. I don't want to go through all the formulas, but if you write down your equations in your quantum mechanics and you vary the potential, you can get a Hamiltonian, and this is very much like the AC Stark effect. That's all I'll say about that. And you can get these extra side bands on your energy level. So this experiment, this is the joule. You can treat these things like a joule. Here is a solenoid. This solenoid has a spatial current, and at this boundary, that shields the magnetic field from coming out because it's like very long. And so outside you have an electric vector potential with no magnetic field. Inside you have a non-zero vector potential and magnetic field. This is the temporal version, where you have a time-dependent charge on this surface, and inside you have no electric field but a time-varying potential. Outside you have both. So the question is how you can generate this in an experiment. So if you bring two plus charges up, in the middle you sort of have that, or two capacitor plates, you have that. But what we have, so we have made a cavity. We have made a cavity system that where we can have a time-varying potential inside a cavity without electric field. That's what we have done. And now I'll explain how we did it. what you have here is a capacitor mode in a cavity. That's the TM010 mode. It's exactly like a capacitor. You have plus and minus charge, which oscillates, and there's current around the boundary that puts plus or minus. It's basically a high-frequency capacitor. So we decided to do this, where we made 3 cavities in a row separated by these really thin foils, less than 8 micrometers, and we put little tuning rods so we could tune them all to the same frequency. We made these a little bit different dimensions so we could tune them down and get them all at the same frequency. So what's the idea of this? The idea is that we can control the charge going on this foil via this interferometer excitation, which looks like this. We split the microwaves. We have an attenuator and a phase shifter. So it's like a Mach-Sedner interferometer, but we have these 3 cavities here, and we have these really thin foils. So what happens is these input cavities will put charges on these foils, and that then excites this cavity. These foils are just like microwave coupling, but they're resistive. When you put a probe in, it's reactive, right? So you could never do this with a probe, but if I put a resistive foil, that's a pure resistive coupling into the cavity, purely resistive. And so that's how we excite this cavity. We've done a model now, a circuit model, and we can fit the data exactly, but that wasn't in the original paper. So this is a balanced interferometer. So the magnitude of charge oscillating on the foils is the same. Then we can just vary the phase. So what happens when we do this? Here's an example. If we're out of phase, you get an electric field and you have opposite potentials on each foil. If they're in phase, we have the same potential on each foil. And if you integrate over the volume, the electric field goes to 0, and it's 0 in the middle and is very weak here. So we did this, and the interesting you get when you're in this condition, when you're out of phase, you get this resonance, and then as you change the phase until you get to this, then you get this extra dip. And this extra dip is an electromagnetic induced absorption, and it occurs because when you're on resonance, this system doesn't allow you to have an electric field in there. Okay, so what we have is in a very interesting situation on this dip where we've got an enhanced time-varying potential by the Q factor, but no electric field. And so classically, nothing can come out. But if we can put a quantum system in there and try this and see if we can see something, that's the idea. So, you know, I'm not sure on that measurement yet. We proposed something in our original paper, but in that original paper, the problem is this Aharonov-Bohm phase is global, so you've got to get a difference between energy levels. And in the gravitational effect, that's easy because we've got another paper on the gravitational effect. Rabi oscillations change the mass of your atom. When you're in the excited state, your mass is different, and that's easy. But this is a little bit harder. We think we can use MV diamonds. We think we can use maybe some sort of charge qubits, but we haven't quite worked out what we can put in there yet. But the key point is that this phase shift is 30 times better phase sensitivity than the Q. So if you put that as an effective Q, it's 30 times, right? So this can be a sensitive measurement system. You can't really use it in an oscillator because there's no power coming out, but you could use it to, maybe you make these foils some acoustic drum or something, or you can maybe make it as a, yeah?
Is it important that you have 3 cavities?
Yes.
So can I think of this as like a triangle arrangement where you get a kind of phase?
Yeah, yes, because I've thought of the optical version too, or maybe that's what you need if you want to do it in optics.
Okay.
Yeah.
Okay.
Some sort of triangle arrangement with some sort of output, but you need a way that it cancels on resonance. So this is because we're using charge, and we couldn't do this with an inductive coupling. I don't think so. Because we can't. The modes would strongly couple, and they will have to be the same frequency.
So I know you get something analogous in current through like a molecule with 3 sites where you have a dissipative tunneling process that goes in and goes out, but you have coherence in the 3 sites, and then you get this sharp dips that are like a little bit like these EIT resonances, but I don't know if it's related at all.
It could be, but this was totally unexpected for me. I just started building this because I thought this might give me this. Then when I saw this, I thought of, oh yeah, that's obvious. Makes it 0 on resonance. But I think this is a really interesting, and there may be other versions of this in other domains. You might be able to do something similar, right? Okay, so I'll continue on. So here's some more information. So this is where we tune it, and the better balance you get, the better phase sensitivity you get. We don't know what the limit is, and so at this point we have a time-varying potential with no electric field right on this point. If we just slightly detune, it disappears because they have to be tuned. And large detuning, we can see the 3 modes separately. They're all going through. And if we put 50 micrometer foil, we has no effect. It's too thick to be able to get energy through. So you need a foil for this. Yeah. Okay, now I can talk about some magnons stuff. And so these reentrant cavities. So I'm going to go over past work we've done, and I'll mention a bit about what we're looking at in the future. So these reentrant cavities, which I use for the gravity wave experiment, are quite interesting, especially when you bring more than one post, because this double post structure, you can have the electric field in phase in the gap or out of phase. When it's in phase, they act like a single post and all the field is outside. But when they're out of phase, you can put a lot of field inside your sample. So this was quite interesting. We got a magnon sphere from a colleague, originally from Russia. Can't get them anymore. And we wrote this paper. So we put the magnon in there, and you could see that you have the bright and dark mode when you do the mesh of this system. And then when we did the experiment, this is basically the experiment. We have it cooled to millikelvin temperature. And then this is what we call the dark mode when they're both in phase. There's virtually no coupling to the Cattell mode. This is a Cattell mode, this M1. It's just going through. But there's some other symmetry. There's other modes which match the symmetry of this that have some sort of coupling. But when the Cattell mode goes up and gets to this out of phase mode, there was a huge coupling on the order of a couple of gigahertz mode separation. So when we first measured that, we were sort of a bit out, it took us a bit by surprise, but we know coupled mode theory, and yeah, it was, we knew why it was happening, these huge couplings. We also put a diamond sample in there, did this experiment. It was meant to be NV diamond, this sample, but we just coupled strongly to P1 impurities. There were more of them than NV. We only coupled, and we got strong coupling between these P1 centers quite well. And the NV was very weakly coupled, so the sample wasn't very good. But anyway, we published that and showed that this, if you got a good sample, we have a good sample now, but we haven't done anything with it yet. You can probably get really strong coupling between those MVs. So we then started looking at more posts, and so I looked up the literature, and if you have more than one photon mode coupling, people seem to call that super strong. So it seemed like good to put in the title. So we did that, and we were able to mimic with just posts time reversal symmetry breaking with it, like in whispering gallery modes, and this super strong coupling. So this was the results. So these, when we made a pattern of these reentrant cavities in a circle, they sort of resembled this time reversal symmetry breaking of two doublets, like these two doublets here, which are roughly the same frequency as long as you get the dimensions right, where one mode coupled strongly and one mode didn't couple at all. Okay, so this was just using these posts, and then with these ones, when you put them in a row, you could get sort of like similar to something with a free spectral range, and you could couple to them all at once. So that's what that paper shows. There was some more work that we did. We also look at lithium ferrite. Lithium ferrite's a very interesting alternative to YIG. It seems when you're at low fields, it doesn't start from zero, it starts from somewhere up here, and you can see it more clearly at low fields compared to YIG. And yeah, it sort of turns around. I'm not an expert on magnetism, but anyway, we measured this, and we also did a loop gap with a YIG, and we measured this slab. This was really extremely. This is just a reentrant cavity with a slab of YIG, a big slab of YIG, and I've argued with the people in my group. I think we got some deep strong coupling, but other members of my group don't. Right? I don't know if anyone's got deep strong coupling in a YIG system. No one's. But if you look at this, so this is interesting too. So at low magnetic fields, these are some higher order modes. Some of them tuned down and some of them tuned up. So there's some sort of phase transition around here, and down here is lossy. I think we think this is something like spin-spin interactions, but I'm not really sure because I'm no expert. But you can see that there's this effect where your photon modes want to tune down or up, depending, and down at low magnetic fields, the YIG is very lossy down at low frequencies here, at the low frequencies. So there's some sort of physics going on there. But when you look at this, this second branch only appears up at this frequency, and when you look at this and you fit this part of the branch, you can easily fit a deep, strong coupling to that. And then the curve changes direction, changes slope, and it seems to be this typical two-mode coupling. So when you have deep, strong coupling, you only get one mode. The other one is not there. But it could be just due to loss, but not certain. But I can easily fit something there that gives me a coupling greater than one, right? Which is deep, strong coupling. But I haven't published that because, everyone in my group argues with me and says it's not. The other experiment that we have done is we've excited these YIG spheres, a really large YIG sphere of 5 millimeters. So this large YIG sphere is interesting because you can get modes in this sphere, and we can look at the modes in this sphere, not just in some sub-wavelength regime, but this becomes a resonator itself. So we did that, and you can see that there's some modes on here. There's that same effect where as you take up the magnetic field, and it's about the same magnetic field, where there's these interactions which take some of the photon modes down before they turn into magnons, before they become strongly coupled to magnons. And we down here, we can measure the line widths of some of these magnons, and they're all around a few megahertz. Fairly good. It's a big sample. And then when you look at this in detail, you can see the different photon modes in the sphere coming across to the other side of all these magnons interacting with these photon modes in that sphere. And the best coupling that we get is about 6.2 gigahertz in this system. So they're getting really large, okay? In these systems, because you've really got your photon all in the magnon sample. And this is interesting with these higher order modes. You definitely see some phase transition. Just asking, does anyone know what? I think we said it was spin-spin interaction, but we're here at this magnon workshop, and I guess everyone's seen this in their measurements. That's my question to everyone. No. I was hoping someone would give me some insight, but I think we said it was like spin-spin interactions. So this is at the low magnetic fields where YIG is particularly lossy. Well, at higher frequencies it's not. But and then when we polarize all the magnons away, we can measure the permittivity of YIG. And that's what this measurement is. When we got really high magnetic fields around 7 Tesla, we can look at all the modes and we can iterate the permittivity and the difference between a few modes and what we measure, and they all converge on this spot, which is good, which it tells us the permittivity is just under 16. So I think that's a bit of useful information for people who use YIG. We know what the permittivity is from these measurements. We spend a lot of time measuring permittivity of different crystals. We also measured lithium ferrite in these 2 post cavities. We made 2 different cavities, one at high frequency and one at low frequency, just to understand lithium ferrite a bit more. And yeah, so mode softening was observed at low magnetic fields coming up from around 6 gigahertz here. So the interesting thing about the magnons and lithium ferrite is they're not starting from 0, they're coming down and turning up. This is not a too different field from where the YIG start. They go down, but it's much lossier than go up. So it's less lossy. So this made it, so this is a sort of useful property of lithium ferrite. What we were interested is using this as a sensor for magnetic field. So we did this work where we put the lithium ferrite in a superconducting cavity and used it as a sensor to see how the magnetic field would get into a cavity. So this was niobium, and you can see as we change, we've got this resonant frequency is very high up here around 20 gigahertz. We're in the dispersive regime of the magnon, and as we change the magnetic field, we see the magnon frequency doesn't change. That means there's no magnetic field in here. And then we get to a point where we reach the critical field and boom, some field is let in. And then there's some other field where it just becomes like a normal conductor, I guess, and just starts going up. So we could measure, so I think this is really good. Well, YIG would be a bit harder to use because, or maybe you can use YIG, it's just a bit lossy at low magnetic fields. Depending on the frequency, but that's why we use the lithium ferrite. But this became a great sensor, and this is really important for things like. You got a question.
I have a question regarding this plot. So, if you now tune the field down again,
yes.
Can you see either captured flux or residual magnetic fields in your cavity?
Yes, I think we did that. One of these might be going up and down. Ramp up case, this is ramp up, and then we've got ramp down. So this is ramp up and this is ramp down. So you can see how it changes.
Okay, thanks.
Yeah. That's exactly right.
And it goes back to the initial value.
It's not quite back to the same place. I think there's effects of vortices definitely in these measurements.
Okay, thanks.
But the point is, if you've got a superconducting system and you want to know how magnetic field leaks in, these are very good sensors. And the Axion community really need to know this because they want to start building superconducting cavities with less loss, and they want to know. So this is the way we've proposed. Fermilab have a really funny way of doing it through measuring temperature or something. Okay, and this is where the YIG was originally there's a lot of work on YIG because of oscillators, right? There's a whole oscillator community. So we've got a student working, actually, we've got a whole bunch of YIG filters, and we're going back to oscillators. So this is a paper he's about to submit, where we've got, you can buy these multiple YIG filters. I think they're from China, about 7 in one, and they're filters, and they've got really steep slope. So what we've done is put 2 in to make a really high Q resonator like this with the steep slopes, and it works. And we apply Leeson's model, and we get lower phase noise due to doing this. There's a bit of attenuation here, but that's all right. So we've just crossed the 2. And so that will come out sometime this year, but I just show you some data that we've got using YIG. It's not really to do with magnons, but it's using YIG. And back to the roots of YIG being useful for oscillators. Okay, now I want to talk about these cavities. So I'm going to talk about a new microwave cavity that we've invented. It's a cavity which has bulk chirality, bulk helicity in them. So at the moment, this was published in 2023. The reason we invented these resonators because when you have helicity, you have non-zero E dot B, and that's what you need to be sensitive to axions. And then we realized there's probably a lot more things we can do with them. And this is on the archive under review, which explains more about the helicity, explains that so what happens is we twist boundary conditions in a resonator, and explains how it's like a chirality parameter, and in the end you end up with helicity, or you could think of it as an axion field. And this is not submitted yet. It'll be submitted soon. It is under preparation. So let me talk about these. We call them anion microwave cavities. Well, I'm not sure if that will stick, but the reason we did that in our first paper is because there was this paper in PRL. You use classical Mobius ring resonators which exhibit Fermi boson rotational symmetry. So the fermion rotational symmetry comes about if you have a flat thing and you twist it. It has fermion symmetry, the rotational symmetry, not the modes, but it's fermion symmetry. And that's because if you have this structure, no chirality, there's no difference between spin up and spin down. But if you put a twist, then it depends which way you've twisted it, whether it's left-handed or right-handed. Okay, so they called that this fermion symmetry in this boson. And however, for both cavities, we started looking at these, thinking that the modes might have helicity, but when we looked at the cavities, there was 0. So even these cavities had 0 helicity. So what we realized is that this is boson, this is fermion. We developed this anion rotational symmetry, and this means that you change the cross section. You could have the cross section D3, D4, D5, D6, and this you get, and you can get this rotational symmetry. And when you twist it, this is now we can say as anion rotational symmetry because the twist is not plus or minus pi or 0, and that's anion. So we call that anion rotational symmetry just because of these papers exist. So at these cavities, so why the triangular cross section? So you can do a counterclockwise twist, and the cross section. The reason why we choose this cross section, because you can imagine as you get more and more sides and you twist it, nothing happens. So you need the minimum amount of sides for this. And we showed that as we twist, you can calculate the helicity, which was that formula before, normalized E dot B. And you can see as you twist, the helicity goes up and hits nearly 1 for this triangular cross section. For a square cross section, it's still pretty good. By the time you get to polygon, it's not very good. So you can use a square or a triangle. And so how do these generate helicity? Well, if you take a triangle cross-sectional mode, you have different modes. You can have T and TM. Some of them are degenerate. If you take this triangle, and when alpha equals 1, these modes are degenerate, this TM10 mode and this TE11, and that they're exactly the same frequency. As you twist it, they strongly couple, and they strongly couple into plus and minus, TE plus or minus TM modes. And then they tune, and then they have helicity. One has plus helicity, one has negative helicity. So this is a twisted boundary condition. And you can see some of the modes there. So yeah, you can see one mode has a helicity up to 1, and this is -1. This higher frequency mode, it has more spurious a mode, so sometimes it gets degraded because it gets interacting with the spurious mode. So one tunes down, one tunes up. The one tuning down is quite clear because there's nothing down there. The one that's tuning up runs into spurious mode. So that would be the difference between these two. So here's an example of experiments where we've got here, this is a simulation, and the color plot shows helicity. Oh, I didn't put the scale, sorry about that. And as you tune them, you get some modes tuning up and tuning down, and some modes tuning up, and you see mode interactions as it tunes up. The funny thing is, when the modes interact with another helicity mode, negative, they hybridize to give no helicity. So here's an example of if you take a VNA and look at these structures, you can see that when you don't have a twist, here's the modes you get when you twist it. You can get these degenerate modes, tune in frequency, and the one that twists one way has its plus mode here, and the other one that twists the other way has its minus mode there. So that's where we call this plus or minus. So yeah, can we build these geometries? Yes, we use selective laser melting. We can make them superconducting by using aluminium and then annealing, and we anneal them to get rid of the carbon. And we've built cavities like that before with quite good Qs. We know the frequencies, we can calculate their helicities and the geometry factor of how well they couple to the walls. We have a ring resonator, which is like a Mobius strip, or we can do them in a line. The ones that are like a Mobius strip, which are harder to build, have generally better geometry factor. You can see here if I make it a ring or linear. How you do that is a bit, is not obvious. So here's an example of our simulations and measurements, and they're spot on. So we know that we're pretty confident with the modes and the way they work. And here's the Mobius. So the Mobius has more modes with high helicity. This one's equivalent to the TE plus or minus TM, and they go around in a circle. They're quite interesting. This is the first one we had 3D printed. It looks quite nice, but when we went to drill a hole in to couple to it, it was solid. You couldn't make it hollow. You have to make it in pieces. So now we've made it in pieces like this, and we make each piece separately, and we can couple it. We can, put knife edges and make them very good. I don't have our results on that yet. We were going to cool them down and measure the Qs. Our student put it into anneal first to get rid of some of the carbon, but this is a lesson in units. Whether you use Celsius or Kelvin, you press the Kelvin button and the thing melted and broke the glass tube. You can't tell students off for that, can you? Because at least, just use the wrong units. So now we had to buy a new tube, and we're getting it made again. But otherwise, I might have been able to report to you. So another thing is, the question is, can we couple helical modes to magnons? And that's the first thing I thought of. So we had a student that looked at that, and the interesting thing is we came up, this is not published, this is just a master's thesis, this is Ashley, who did the work, is that there is a specific sphere position that produces circularly polarized unidirectional resonant mode propagation with electromagnetic helicity. So in other words, a traveling a wave around with helicity. There's a select position you can put. We worked that out, but nothing published yet. I'm just giving you a preview, since in the spirit of people showing stuff. Yeah.
Sorry, just a simple question. So the functionality you're describing, excuse me, is effectively a circulator then, or an isolator. So you put the sphere in, and then in principle you have two counter-propagating modes that are degenerate, and you can break that degeneracy with the Yig sphere.
Yeah, well, there will be, the Yig sphere in this case allows it. So there is some, it's quite complicated, but so they sort of travel around like standing wave patterns, right? Otherwise, but in this case, we can get them like a pure traveling wave going around just in a single position. We had to use a supercomputer to find the position. Just put it in all different positions until we found. I know this is Jeremy Borhill, who worked with Vincent in France. He'd done some similar work with just a torus, and he wanted to do this and see if we could get any special position that would give us some special result, and it seems like it does.
Thanks.
Now, that's the work on magnons. Now I'll just, for the last part of the talk, I'll just talk about our normal ESR. I'm not sure how I'm going for time, but when we first got our dilution fridges, the first thing we did was cool sapphire to low temperatures, and then apply that so you can get multiple modes. So we call this whispering gallery mode spectroscopy. So we can put our sample in, and every line across here is a mode, and every time we see an interaction with an impurity, these impurities are parts per billion, we can put a cross. So then we can look at the Hamiltonians, and we can see what we've got in this crystal. So in this case, we have Fe3 up. So we can measure very precisely impurities in samples, and we're very interested to do this for a range of samples that are of interest to different communities. We can see chromium, Fe3+. This is meant to be pure, but of course it has impurities. There is one unknown species with a very high G factor, probably rare earth. And this is the sort of thing you see. You see this from the whispering gallery modes come in doublets, and when something like Fe3+ interacts with it, you can get time reversal symmetry breaking, where one mode gets one mode. So what you get, usually in sapphire, because there's a lattice, a mode traveling this way will backscatter, so you get two standing waves. But when it crosses the Fe3+, it forces them to be different, so now you get traveling waves going around. And so that's what you see here. We can actually, and then actually you can look at it like conservation of angular momentum, where the left one and the right one, depending whether it's upper or lower, will interact with the spin. So we look at a mode here and we look at a mode there, but are pretty much the same frequency that interact pretty much at the same magnetic field. When you go to low temperatures, you get interesting effects because the higher frequency mode condenses out, and all the spins go in the larger one. So one of them gets less coupled, and the other one gets more strongly coupled. That's just because you can't populate the higher frequency. And this is interesting if you do it as a function of power at millikelvin. If you just measure a mode, you can see that the Q drops by over an order of magnitude. That's because of these two-level systems. All these parametric impurities act like two-level systems in your system, and even if they're way off the tail, they will cause loss. We have measured the losses on the order of 10 to the minus 5. We've also measured rare earth in YSO, and we found some new transitions that weren't known. We still don't know what they are because they're not in the literature, but they have zero field and ion group type transitions. These are all the rare earths which are doped, but these transitions here will be, they weren't intentionally doped. But we managed to get strong coupling between those unknown transitions, which was interesting. The most recent work that we did is on calcium tungstenate, because that's a new sort of new material that's sort of widely interesting. And we saw in this sample, we saw a whole lot of impurities. I think the manufacturer used a dirty crucible for this one. We got another sample, which is from guys in Munich who make these crystals for a dark matter experiment. We see far less, and the Qs are much better. And we've now, no one's ever measured the permittivity of this sample, so our next paper is going to show what the permittivity is. And I don't know if I've gone under or under time, but that's all I prepared. So that's we can. If you've got any more questions, I can answer them.
Are there any questions?
So thank you for a really inspiring talk. I guess one of the things that I wanted to ask about is a kind of experimental thing. Can you say a little bit about the post cavities and some of these structures that you're making that are extremely high Q? Obviously, the manufacture of those cavities is crucially important, and there must be some secret sauce. And I'm not sure, what it's not easy to articulate these things necessarily, but can you say a little bit about how you learn to make these things? And
okay, so for the dielectric resonators, it's really dependent on manufacturer, and you really want low impurities. And I think there's been some work, because sapphire's used a lot for substrates for qubits, and they've basically come up with the same conclusion, I think. And so there used to be crystal systems in Salem, Massachusetts, who made these really pure samples. And the interesting thing is, when you've got these impurities in there, they can be active, because it can act like a maser. Because we actually made a maser. I didn't show those results, but with Fe3+ in there, you can pump at 31 gigahertz, you get 12 gigahertz out. And what we've found is when we're building a really low noise oscillator, low phase noise, if we've got any chromium impurities in there, then you cannot get low phase noise. So this is really crucial. But the problem is this for these materials, it's getting lost, the ability, because I think they changed their name to, I can't remember what their name is now, GT or something like that. And they don't make the same high purity they used to. And then we bought samples from around the world, and we just can't get the same purity. So you can lose technology like that. When it comes to when we do the superconducting ones, we just have to get good niobium. We generally get that from Germany. There's a company in Germany that makes RRR or something, niobium. I can't remember what they call it. But then there's there's some results I didn't show where we're using isotopically pure silicon, and that really has to be high resistivity, and we can get ensembles in there with very high, I think with less than 11 kilohertz line width ensembles in there. So it's just the materials, really, and then polishing. Polishing is extremely important to get high Q. You have to think about polishing. It could be electro polishing or just in a tumbler or something. But yeah, we're working on all those things now because we want to make these twisted resonators very high Q. So we need to get the surfaces. We're concentrating on getting the surfaces really nice. Yeah.
I would have a question regarding calcium tungstenate with respect to sapphire SO. So you certainly looked at the dielectric losses or the loss tangent of this material versus sapphire. Can you comment if this is compatible?
Yeah, we're just about to submit a paper on that, where we've measured this large crystal of calcium tungstenate, and it's very pure. And the Qs are pretty good. They're not as good as sapphire, but they approach 10 to the 8. You can get some really nice. I think if you have spins in sapphire, it broadens them, right? Then calcium tungstenate's less broadening. I'm pretty sure we've got some strong coupling with impurities in there. We just haven't. There was this result. I believe this was strong coupling. We just didn't do the span big enough. But everything told us that it should be, and we couldn't claim that because no referee would allow us to.
Okay, thanks. Maybe another question. So your foil cavity, given the fact that you're reaching ultra high Qs in there, did you also look into the mechanical modes of the foils?
No,
because
but I want to.
This changes the boundary conditions, and you should be very, very sensitive with that.
Yeah, the thing is, though, it's resistive coupling, so I'm not sure if it would do it like, oh, yeah, I guess it should because it's making the cavities. Yeah, let me get back to that. I think this is one of the most interesting things I've done, I think. Yeah, you're right. I think they'll be very sensitive if you put some sort of drum mode in there. And that's what I want. I was thinking that's something I want to do. Haven't quite worked out what I want to do yet because this paper's only just been published. But I've also got another idea to string cavities together for dark matter with foils so they all couple together at the same frequency. Yeah, that's interesting. I think I didn't expect to get these results, but when you look at them, you realize that that's what you should get. So it's it was a harebrained experiment I got an undergraduate student doing who's now doing a PhD, but I think this is an extremely interesting effect. It's how you get electromagnetic induced absorption. It's just a classical system. You're getting this extra absorption just because you've excited like an interferometer. I want to do it with superconductors, actually. I think that'll be superconducting foil will be extremely interesting. Maybe one of you guys would try doing it as well. Yeah, it could be a very sensitive interferometer, but you've got a lot of degrees of freedom to take care of. That's the problem with it. You've got to have the cavities tuned. Tune the phase. So it's all doable. Just a bit of effort.
Do we have any more questions? If not, let's thank Michael again.
Thank you.